Yeah.
It's not always Simon's, but
Yeah.
certainly here at Berkeley.
No, I was on sabbatical here, actually, so it is.
Okay, so I'm all right. I'm not. We have Jessica Hullman coming in from Northwestern. She is the Ginny Rometty Professor of Computer Science and a fellow at the Institute of Policy Research, a place near and dear to my heart at Northwestern, and has done, well, research all of the topics we've been talking about for this workshop. So I'm really excited to hear what you have to say for us today.
Okay, thank you, yeah. So yeah, I thought I'd give kind of a talk that's going to cover a few papers, so it's a little higher level, but I want to talk about some frameworks we've been developing using decision theory to try to get more insight into human AI collaborations, including what's going wrong and how can we potentially improve these. And so I would say that the motivation for the work we've been doing in my lab for the last maybe 2 years is a few robust empirical observations. So the first, dating back to like 40s and 1950s, observed by authors such as Paul Meehl, is that when you have some decision task or prediction task in some domain where you have human experts, like medical decision making, if you train a statistical model on what you think the relevant data is, so you get some historical data, you train the model will do as well or better than the human experts. And this is very robust. There have been meta-analyses showing this across many different studies. And on the one hand, as Ben mentioned yesterday, this is not super surprising. So by the time you identify like what are the relevant features, what is the actual outcome we're trying to predict here, and you train a statistical model, then it's going to be hard for humans to outperform that because you're sort of defining sort of optimal learning from that data for minimizing loss over the population, if that's your evaluation criteria. But I think it's sort of disturbing to people because we do have such strong intuitions about humans having valuable information. They might have private information that's hard to encode in a statistical model. They can interact with the patient. They can observe, these features that would be hard to encode through gesture, et cetera. And so today we see attempts to get the best of both worlds by pairing humans with AI models. And the goal, if you look at a lot of the literature, is what is called complementary performance. So we want to see the AI-assisted human do better than the AI alone or the human alone. But there's another robust result from studies over the last 10 years or so where people have been doing many studies to study humans who are assisted by AI. And what we often see is more like this. So whenever the AI is a higher performance in that domain than the human, then we tend to see the human with the AI doing worse than the AI alone. And this, has inspired a whole bunch of different attempts to sort of intervene and improve the human's use of the AI. So we have many explanation techniques and other interventions which are generally based on researchers' intuitions about what might be going wrong and what might help. So my goal in the kind of work I'm going to present today has been to try to disambiguate certain sources of confounding in these kinds of results by using decision theory to sort of first formalize like what is the actual decision problem that this human is facing, and then examine their observed performance relative to decision theoretic sort of benchmarks that define kind of the best case decision making we could see in that situation. So let me start with some work we did trying to address this question of appropriate reliance on AI. So a lot of authors were asking, are people appropriately relying trying to show that, in fact, we see a lot of over-reliance. But one of the problems with the typical sort of evaluation setup is that you might get a result like this that we see a lot, where the human with the AI does worse than the AI alone, but it's often unclear sort of exactly how bad this is, because we don't know what was sort of the best attainable performance on this decision problem that we could have seen. So is that truly what the AI did, or was there actual room for the human to add here, and they really failed badly? And similarly, even when we see the human with the AI doing better than the AI alone, we still don't know how good this is. So, are they pretty close to the best possible performance we could expect on this decision problem, given the human's knowledge, given the AI's knowledge, or is there still, a long way to go? And one of the problems in a lot of these studies that have established this sort of finding that humans are bad at relying on AI is that they use as the measure for evaluation measures based on post hoc accuracy. So they're sort of assuming that the human who is appropriately relying will always agree with the AI when it turns out that the AI was correct, and will always disagree when it turns out that the AI was incorrect. But there's a few problems with this. So one, typically these are decision tasks under uncertainty. So at the time of the decision maker has limited information, and so getting 100% accuracy in hindsight is often simply not attainable, even by the best case decision maker. Another problem is that this can confound different types of errors that humans can make relative to sort of the best case decision performance. So one type of error is simply they're over or under relying relative to what would be optimal, but there are other types of errors related to sort of when they're relying on the AI that we can't really disambiguate when we're using these sort of coarse measures of post hoc accuracy. And so the goal in this first project is going to be to quantify, what is the theoretic value of pairing a human and a model for some particular decision problem where we have human experts and we have an AI model. And we want to compare that to a lower bound, which is going to represent the best case performance. If you did not have both agents, you only had the better performing agent in isolation. We'll call this the value of complementation, so it's sort of the maximum boost you could get in decision performance on that task if you had access to the additional agent over the better of the two alone. And then we'll observe the actual humans in this domain using the AI, and we will look at how close they come to this benchmark, and we will attempt to sort of diagnose what might be going wrong. So we'll separate out a couple different types of errors by creating another benchmark to disentangle those. All right, so I'll give just sort of a high-level overview of the problem setup here. So we are considering 3 different roles that occur in sort of your typical AI-assisted decision workflow. So first, we assume we have a human. They have some signal. So I'm going to use diagnosis, medical diagnosis, as an example because it's a simple one throughout this. So let's say we have a doctor. They are trying to diagnose a patient. So they have some representation of the instance, some signal, which is the patient's profile information, et cetera. We also assume there's an AI. It has some signal representation, might be overlapping. And both of these agents are, we assume, capable of coming to some independent judgment or forecast about this case. So they both have some independent judgment about what the true condition of the patient is. There is a decision maker who has access to these judgments of the different agents and needs to make a decision between going with the AI judgment versus the human one. And typically in real workflows, this decision maker is the same human who we assume can come to their own independent decision. So we have a doctor and they are making the decision about whether to trust their own judgment or the AI. So they choose which one to go with. We assume there's some utility function or scoring rule that defines kind of good decision making in this domain. So that's just going to be a function that takes in an action and a state and assigns some real valued score. This is a decision under uncertainty. So there's a payoff relevant state, which is going to be what's the true condition that this patient has. And there is a data generating process or model, pi, which you can think of as just the joint distribution over the payoff relevant state and the signal. So whenever we go to evaluate, human AI-assisted decision making, we have to say, there's some distribution that we think captures kind of like the distribution of instances we see in practice, and so we're talking about that true joint distribution for whatever distribution we're evaluating on. Okay, so we want to, determine what is the best case decision that could be made in a process like this. And so to do that, we're going to make use of this sort of convention that's often used in decision theory, which is the notion of sort of the best case decision maker, who's going to be the Bayesian utility maximizing agent. So we assume any instance, that this agent encounters, they're starting with prior beliefs, and we're assuming that they are sort of as well informed as we could hope any human decision maker could be, meaning they have access to the joint distribution for this decision problem. So they know the prior probability that the AI versus the human is correct. You can think of this as. On any given instance, they observe the signal, they update to the Bayesian posterior beliefs, and then they choose the utility maximizing action under those beliefs. So on any given instance from this distribution we care about, this is what the rational agent does. And what we want to do then is define sort of the best attainable performance over that distribution. And so we create a benchmark, which is essentially going to be the expected performance or score under our utility function of this rational agent who, is encountering instances and always, choosing the score maximizing action. We can then compare that to what we'll call the baseline. This is going to be the expected performance of this rational agent if we constrain them to only deciding based on the prior. So they know the true prior probability that the AI is correct, and so they're just going to choose the best fixed action every time they have to make a decision. And so this is what I mentioned earlier, this value of complementation. And so, there's a few ways we can use this, starting before we even deploy an AI. So, imagine we are in some setting like a hospital, we have some new AI model. If we can query the humans on, instances from the distribution we think is relevant, get their independent judgments, and also query the AI, apply it, then even before we deploy the AI, we can ask questions like, well, is there a good reason to combine these two agents here? So we can ask, how big is this value of complementation relative to sort of the baseline performance, the expected score that we'd have if we just used the better of the two in isolation. And I think this is useful. This is useful for researchers too, who are wanting to study reliance, because you sort of want to make sure you're studying a case where there's actually like a reason to combine these agents. So I sort of assume that it's more complex to put two agents together than it is to just use the better of the two in isolation. So humans suddenly have to deal with an AI. If we could do just as well without putting those two together, we should. We can also, of course, use this after we've deployed the AI and we observed the final human decisions, which are A here. So as I said, often we don't even know what the benchmark is. Within this framework, we can define the benchmark so we can see sort of how our human with the AI does. But we might want to understand, if we see that there's still ample room for them to improve, what they're struggling with. And so we can distinguish two sort of qualitatively different types of errors they could make relative to sort of the optimal decision performance. One is that they could be relying on the AI at the wrong rate overall. Relative to the rational agent, the benchmark, which is going to define the optimal rate at which you rely on the AI, our humans might be, overall, relying too much or too little. Another problem, though, is that relative to the rational agent, they might not be relying for these same instances. So if you think about what this rational Bayesian agent is doing, they're going to rely at the optimal rate, and the instances on which they rely are going to be those where there's sort of the biggest possible lift in performance by making the better decision. So you can think of them as sort of sorting the instances and taking the top K that correspond to the optimal reliance rate. They're sorting them based on the difference in expected performance of going with human versus AI. And so the human could sort of mess up that sorting step. They can't really discriminate at the instance level, when it's really in their best interest to go with AI. So the way that we can try to disentangle these is by creating another benchmark, which we'll call the misreliant rational agent benchmark. And this is going to simply be the expected performance on our decision problem of the rational agent when we constrain them to rely at the same rate that we observe the humans relying on the AI. So this misreliant benchmark we can then look at, and we can look at the remaining span between the rational agent benchmark and this misreliant benchmark. And this gives us sort of an estimate of like how much loss in performance here is due to the fact that humans are simply over or under relying relative to the optimal rate. This remaining span between the observed human AI performance and the misreliant benchmark is then a measure of sort of how much score or utility is lost because they don't know when to rely, or they're having trouble discriminating at an instance level when it's the biggest sort of difference between the human and the AI. Okay, and so, why is this useful? Well, one of the things, besides sort of looking at existing studies and trying to figure out what was actually going on, I think one of the things that is, often challenging is that you might have some human using an AI and you know that they could do better, but you don't know like what to even intervene on first. So, I'm not going to be able to sort of change the interface, without probably affecting both of these types of loss. But the high-level idea is that if I know that like the bigger source of loss is reliance loss, that might mean that the interventions I think about are those that are going to like help the human trust the AI more or less in general, like maybe some basic education. Whereas if it's discrimination loss, I might take a closer look at the actual interface that I'm using to present the AI prediction, think about like how do I help them at an instance level better weigh like their own sort of knowledge versus what the AI is giving them. And so we can apply this to existing studies, which we've done. So we've taken some, highly cited papers on, oh, sorry.
Quick question.
Sure, yeah.
On the previous slide.
Yeah.
Is it clear that the reliance laws and discrimination laws are totally orthogonal? Because it seems like when the human has trouble distinguishing at the instance level, it will.
Yeah, no, they're not, is what I'm saying. They're not totally. I mean, we're just measuring sort of like, if they had relied perfectly rate-wise, how much better would they have done, and then trying to separate that. So it's just sort of, I think of it more as like hermeneutics. Like we're trying to just like get an interpretation that will allow us some insight into what might be going on rather than sort of, these clearly separable things. So yeah, that's important. Tennis Schmitz, okay.
Just one clarification.
Sure.
The reliance, is it the joint probability of disagreeing and the human following the AI, or is it conditioned on disagreement?
Yeah, it has to be conditioned on disagreement because you can't really talk about reliance when they're both saying the same thing. So yeah, we're only looking at those cases where they disagree. That's a good question. Okay. So yeah, I guess very briefly, we can apply this to existing studies. One of the things we see is that some of these really well-cited papers, like the potential for complementarity is low to begin with. This is not an example. This was a study by Bonsall et al. They had a few different tasks. One of them was like LSAT performance, which we're looking at here. And so you can see that like the green versus the dark gray gives us the value of complementation, and it was pretty large here, so this was a good situation to study. But when you look at the behavioral performance, there's still sort of a long way to go towards sort of the best possible performance these agents could have seen. And so when we then create the misreliant benchmark, we see that overall, people are not losing out on a lot of sort of performance because they're over or under relying. It's actually more related to their ability to sort of discriminate when to rely, or when it's kind of the biggest gain. And this was in contrast to sort of how the original authors interpreted their results. They said this was really just a problem of reliance. And so, we can sort of get more insight into the existing literature from these kinds of techniques. All right, so in the remaining time, let me briefly talk about some other directions in the same sort of space of applying decision theory to try to figure out what's going on with humans and AI. I'm going to go back to this original question I started with, which is that, and just sort of emphasize that often, we think that humans have some additional valuable information, but it's often very ambiguous. What is that information they have, or what is the value of that private information they might have? How might they be using the available contextual information relative to AI models? Like, are there features that they're not exploiting as well as they could? These kind of things are often hard to get some insight into. And so in this last project, we were mostly just evaluating information value, and we were looking at this sort of very constrained decision problem where the decision is simply to go with the AI or the human, and defining the value of complementary information that way. What we now want to do is just slightly generalize this. So we want to be able to say, like, what is the additional boost in best case decision performance we could get if we go from sort of the rational agent who observes only some set of agent decisions for this problem to the rational agent who observes those agent decisions and some additional subset of information that is contextually available. So maybe we want to know, like, are the human decision makers, do they appear to already be sort of using information synonymous with some feature that we know is available to them? We can ask questions of that form. Again, we're assuming a data jarring model here, which is just going to be a big joint distribution. And here you can think of, we have the agent decisions, and then we have a bunch of basic signals, which might be like features of the instance. There might be other agent decisions that we treat as a basic signal. But the idea is we want to condition on some focal agents and figure out the value of additional pieces of information. And I guess an implicit assumption here is that we use is common in information economics, which is that any information that is available to an agent will be revealed through variation in their judgments. So that's why by looking at the decisions that the humans or the AIs made, we're sort of getting a sense of sort of the information that they have access to. All right, so yeah, there's various questions we can ask within this kind of framework, like, what available contextual information are they not exploiting that they could, potentially get value from for this decision task? What is the value of the human's private information after we already observe, all of the features of an instance? It's a way of sort of getting a sense of, like, are they bringing something that we are not aware of? And we can do things like try to compare information use between agents. I should mention that, like there is some nuance for this kind of thing. So one of the things, that you have to do is decide what are the basic signals in your environment. And so if you have like very high dimensional, signals like images or text, typically you want to use sort of some coarsened set of features as your basic signals. So there's, with high dimensional signals, there's like an extra degree of freedom. And so typically you would want coarsened signals that are kind of like human interpretable. So some of the work in like the interpretability community becomes relevant here. Another nuance, though, is that like when you see that this agent complementary information value is small, you sort of have to be careful in how you interpret it. So let me just give an example. So one of my colleagues at Northwestern has done studies with dermatologists, both sort of specialists as well as primary care physicians. And one of the questions they were interested in is, do these dermatologists appear to be using skin color when they make diagnoses? And they had an AI model as well, and they wanted to sort of get a sense of like, how much were these dermatologists potentially, responding to skin color relative to this model. So we can do this kind of look at the agent complementary information value where we condition on different types of human agents or an AI agent and see like what's the added value of skin color for this decision problem. And what we found was that the ACIV was smaller for these humans than it was for the AI model. So the AI model, had more value to gain from this skin color. So it was, to some extent using information, or not using that information as much. But because ACIV is small for the humans, that might mean that either that signal doesn't have a lot of relevant information for the decision problem. So it could just be that it's not useful, like it's not going to help you, figure out the right decision, or it could be that they are already using that information or equivalent information. And so, you sort of have to, to interpret what this means, also look at the independent value of the signal to try to get a sense of like, is this actually a valuable signal for this decision task? And then you could try to sort of disambiguate. So there's a little like nuance in the interpretation. You can't just conclude like these agents must be using this signal. Okay, so I'm probably running out of time. I'll just briefly highlight a few applications. So I think, for a lot of this work, we're trying to get insight into what might be going wrong or what humans might be leaving on the table in order to intervene. And we want to intervene, and then we want to see that we can actually improve decision performance. And so some of the ways we've used this complementary information definition are first to select models. Often we have multiple highly performant AI models that we could deploy to help, say, doctors. But we can look at, which one is likely to offer the most complementary information value. And what we find doing this for a few medical tests is that often the best model in terms of accuracy is not the one that's going to complement the humans the best. We can also use this as a way of adapting or designing new explanations that are going to highlight for the human the not just the information that some AI model is using, but the information the AI model is using that is most distinct from what they appear to already know. So I'll just briefly, I guess, show an example. So I think the problem with a lot of explanation techniques is that first, they only explain sort of what the features the AI relied on. So this is a common class of explanations. But those features may not be that relevant for the decision problem at hand. And what the explanation highlights doesn't take into account what we might already have observed about what information the humans seem to have. So what information already appears to be sort of encoded in their judgments. And so we can basically, we define essentially an instance level definition of complementary information value, which gives us sort of a sense of like how much room is there for specific decisions to be improved through better use of a specific signal. I'm just going to skip over the details for time. But what we can do then is use complementary information to, for instance, adapt existing explanation techniques so that they highlight information being used by the AI that is most distinct from what the humans appear to be already aware of. And so this is an excerpt from a SHAP explanation. This last column was just the SHAP values, and I cut it off. There were more features, but we had an experiment where we had people doing house price prediction And so in one condition, we just showed them SHAP. In another condition, all we did was use the complementary information value definition in order to sort the different features, and then we highlighted the top few. And what we found was that we actually saw, measurable differences in decision performance just from this sort of simple, highlighting step. So we were looking at how much they improved relative to independent human judgments, which we collect in these experiments as well. And relative to SHAP, there was 25% more of an improvement simply from passing this through this kind of filter based on complementary information. Final thing that we're doing that I think is sort of interesting is actually trying to design complementary agents, like language model agents, by fine-tuning them using this notion of complementary information values so that they can sort of help humans extract or help decision makers extract information in a text that we have available at the time of some decision that the humans might not be exploiting. So here's just sort of a quick diagram, but what we're doing here is assuming a decision maker, they have some unstructured text available to them. So to use a medical example, we might have some doctor, they have access to a radiology report. They also see a radiology image, and they might see some agent decision, like an AI model's decision. We assume that that text contains latent signals that are relevant for the decision problem. So again, we just have utility function and a decision problem we've defined. And what we want to do is basically fine-tune an LLM using reinforcement learning-based fine-tuning so that it outputs the signals that are relevant to that decision task, which, for instance, might be like cardiac dysfunction, diagnosis, but are not necessarily captured by the information in the AI prediction. So we're kind of trying to show the decision maker, like, here's some stuff that this AI model doesn't appear to be getting. So this, I think there's many applications for these kind of things. So these medical examples, for instance, but we're also looking at cases like, you have humans who are making very tough decisions, like social workers deciding when to remove children from homes, and they have access to a whole bunch of text data, like call transcripts. But any given social worker may be sometimes missing information that's relevant that predicts sort of when the children actually need to get removed. And so that's one. And another one we're doing is looking at Wikipedia article edits. So on Wikipedia, there's algorithmic sort of, or a machine learning model, I think, called Liftwing, that is basically looking at each edit and deciding whether to approve it or not. But then that model's decisions have to be overseen by some actual human moderator. And so what we're doing is, pulling out what's the information in this revision, this article revision, that will most predict whether the moderator should, revert that decision. All right, so I will close there. I think the high-level takeaway is just that to understand human AI or AI-assisted decisions, we really need to sort of understand and clarify what's the decision problem we are studying and what is attainable within that. And then we can start to ask a number of questions about the value of different pieces of information. Thanks.
Thanks so much. Now it's time for one or two questions before the break. Let's start with Rocket.
Thank you. Lots of interesting leads. One question I have, when you have the human, well, let me ask differently. In one of your settings, was there a situation where the human, in order to override the AI decision, had to do work more than just saying, I don't think it's right? Because, and the reason I ask is because we tried to experiment with this a little, and we found that as there's like another cognitive process. As soon as there's more work, they're reluctant to disagree with the AI.
Yeah, I think there's a lot of that. Yeah, and the kind of situations we've looked at. We're not. I guess that's not something that we've specifically tried to understand. We're really just sort of looking at data sets where you have the independent human judgment, because it's becoming more and more common in these workflows to first have the human make their prediction before you show them the AI. So we're just assuming a certain setup and and then running our own experiments sometimes that have this setup. So yeah, but that's I know these. There's lots of
the work anyway already.
Yeah. Mm-hmm.
Part of what you're talking about there in terms of the value of information reminded me of very old work by Eric Horvitz.
Yeah.
Value of surprise for do you think of it in the same line of?
Yeah, I think it's related. Yeah, we're coming more from, I guess, like an econ theory perspective a little bit compared to that, but it's very similar. I mean, it's all decision theory. a lot of the stuff we're doing with defining value of information, there's sort of an area of information economics that does a lot of this. And so some of the assumptions we make are those that are common there, but otherwise very related. And I've talked to Eric, a lot about this. I hope he's a fan. That's what he tells me.
All right, let's take one last one.
Yeah, so I'm curious about something that I think is related to the contextual setting that you were talking about, because it seems like a lot of the settings where people have sort of like high hopes for like human AI complementarity and avoiding this like clinical statistical judgment kind of thing is where humans like actually have more information, right?
Yeah.
And so to get at that, like, do you think that we need to observe the human's full information set experimentally, right? Because then it's like exactly the settings that we want to look at are the ones where we can't measure it well, basically.
Yeah, I don't think you do. I think we're trying to like get at like the most you can do without that. Obviously, that could be helpful, but because I can't tell humans that they are not exploiting some private signal well enough because I don't know their private signals. All I can say is they appear to have more information than say like the full feature representation that is available to the AI model. So you can test for if they have more in terms of value. But no, I don't. I think you can do a lot without knowing it, but certainly you can do more once you know it. So yeah, I'm curious if you have specific examples in mind. Maybe we can chat.
All right, that's a good segue. So let's thank our speaker.
Thank you.
I believe it's time for our break, right? I'm now looking at time for our break. So we'll have a 25-minute break because we started 5 minutes past.